Okay, just wanted to do a quick video on question 10 of the practice questions. This question asks us to find an irreducible polynomial of degree 4 with coefficients in F2, the finite field with 2 elements. And we have to use that to construct a finite field with 16 elements. Okay, so we have to find an irreducible polynomial of degree 4. If it was for degree 3 or degree 2, we would just look for a polynomial without any roots. Because we know if it, a reducible polynomial of degree 3, for example, has to have a linear factor, which would give you a root of the polynomial. Okay. So, we know that if the degree of f equals 2 or 3, then f is irreducible if and only if f has no roots in the field. Well, in this case it's f2. Okay, that's not true for degree 4. You can be reducible and just be a product of two quadratics. Okay, so for degree 4, we also require that f is not the product of two quadratic polynomials. Okay, so think about what could f factorize as. It could factorize as a quadratic times a quadratic, a cubic times and a cubic times a degree, like a linear term. So we still want f to have no roots, and also we want it to have not be divisible by any quadratic irreducibles. Okay, so first, let's write down all the quadratic irreducibles. Okay, so the polynomials of degree 2 with coefficients in this finite field are, well, the finite field has two elements. We call them 0 and 1. So we have x squared, that's what makes it degree 2. And then we could think of like plus 0x plus 0. We have x squared plus 1x plus 0. We have x squared plus 0x plus 1. And we have x squared plus 1 times x plus 1. Okay. All of these are actually reducible. This one is just x times x. It's the product of two polynomials. This one is just x times x plus 1. Of course, this one is just x plus 1 squared. Right? If you don't believe me, well, multiply it out. You get x squared plus 2x plus 1. 2x equals 0. Like 2 is equal to 0 in f2. This is the integers mod 2. So 2 equals 0, so this is really x squared plus 1, telling us that this this polynomial is reducible. Okay, now look at this one. This is our last polynomial of degree 2. If this is reducible, then there's just no irreducible polynomials of degree 2. But we just check, does it have a root? So let's call this f of x. If I plug in f of 0, I get 0 squared plus 0 plus 1. If I plug in f of, that's 1. If I plug in f of 1, I get 1 squared plus 1 plus 1. Modulo 2, that's really 1. In other words, this f has no roots. Okay, so this is the only irreducible polynomial of degree 2. And now we want to find a degree 4 polynomial that has no roots. Okay, so that means it has no linear terms, and also it's not divisible by this polynomial. Okay. And if our polynomial that we construct has no roots and it's not divisible by this polynomial, then it will be irreducible, because that's the only way that a polynomial of degree 4 could factor. It could factor as a product of two irreducible quadratics. Well, there's only one irreducible quadratic, so it'd just be this one squared, or it has a root. Okay, so let's write out what f of x could be. Let's try f of x could be like x to the 4th plus ax cubed plus bx squared plus cx plus d. We want f of 0 and f of 1 to be non-zero. F of 0 is d. F of 1 is just 1 plus a plus b plus c plus d. We want these to be non-zero. So automatically d equals 1. Because that's the only non-zero element of f2. Let me remind you of that. It's because f2 is just integers mod 2. In other words, 0, 1, where 1 times 1 is 1, 1 plus 0 is 1, 1 times 0 is 0, 1 plus 1 is 0, and so on. Okay, so d equals 1. Now 1 plus 1 is 0, so we also need that a plus b plus c equals 1. Okay, so that means like you could have a equals 1, b and c are both 0, all three are 1, a bunch of different possibilities, I guess. Okay, so under these conditions, our polynomial will have no roots. Okay, and now we just want to see, so any coefficients that satisfy these will have no roots, and we just want to see, also we want to make sure that, oh sorry, I should rename this first one. Sorry, let's call it g. We also want to make sure that f of x is just not g of x squared. Okay, so now calculate g of x squared. Turns out that is, you can work it out, but it turns out to be this. Okay. Okay, so an additional constraint is that you can't have ABC being 0, 1, 0, but anything else will work. So, like, for example, so you can't have okay, but as long as we satisfy this, anything else will work. So like 1, 0, 0, for example, is fine. Or 0, 0, 1. So this brings this tells us that f of x is x to the 4th. Let's see, equals 1. That's plus x plus 1. This is irreducible. Okay, it has no roots. Okay, so it has no linear factors. So if it is reducible, it's a product of two irreducible quadratics. But there's only one polynomial of degree 4 that's a product of two irreducible quadratics. It's this. This is just one irreducible quadratic. Okay. So we have this irreducible polynomial. Right. And there's other choices too. And now what is our construction? Well, now we know that an irreducible polynomial lets us write down this is a prime ideal of this ring f2 of x in fact, I mean, we don't need to get into this now, but this is actually a maximal ideal. So this is a field. The elements of this, so let's call it K. So letting alpha just be the coset of x in K. We have that elements of K are what, like A0 plus A1 alpha plus A2 alpha squared plus A3 alpha cubed, where A0, A1, A2, A3 are in the field of two elements. And now how many possibilities for the elements of K are there? Well, there's 2 choices times 2 times 2 choices times 2 choices. In other words, 16 choices. So our field K has 16 elements. Okay, the end. Okay, and that is the end for that question. Thank you for watching.